Hello, everyone. Thanks for attending the webinar today. My name is Melissa Schwartz, and I manage the education team here at TrainingPeaks. I'm just going to go through a couple housekeeping items, and then I'm going to hand it over to Andrew so he can do his awesome presentation. We are going to be selecting questions as Andrew goes through his presentation. Most likely, we're not going to have time for a lot of questions at the end. We are going to just do a little Q&A with a couple of the questions that came up quite often. The questions that we don't have time to answer, we'll put together an FAQ and we'll send that out to everyone. So you guys will hopefully have some of the questions answered. We're also recording this, and we will let you know when the recording is available. I'm going to work on archiving it as soon as this one is finished, so it should be pretty quick with that. And we also will be handing out the presentation. So we'll make that available as well. And we'll put a link for the presentation on the same site where the webinar will be archived. So that's how you'll be able to find it. Also, if you have any questions, there's a question box so you can put your question in there. And then please mute your mics. So if you don't have them muted, please go ahead and mute them. That will help out a lot. So without further ado, I'm going to hand it over to Dr. Andrew Coggan. Go ahead and take it away.
Thank you, Melissa.
I'm just going to go ahead and make you presenter. All right, you should have presentation rights now.
All right, thank you very much. And everybody should be looking at the opening screen. Tonight is the first of 4 webinars introducing a new power duration model that has been implemented in WKO 4. I hope to get everybody up to speed on this new idea by the end of the webinar series, but it's going to be baby steps as we go, which is why I've broken it into 4 sessions. I know everybody is chomping at the bit. They're really interested in the application, but I think in order to fully understand the step forward here, you really need to know the underlying background. So the bad news is you have to, listen to me while I indulge myself. The good news is I've tried to break it into small bites, and hopefully won't put anybody to sleep out there. And I thank you all for attending. So what are we talking about here? When I say the power duration relationship, I'm referring to what in current vernacular in our book, etc., is what Hunter refers to as the mean maximal power chart or mean maximal power curve. And that is the relationship between the power that you can sustain and the duration for which you can sustain it. And here's a couple example, or an example of somebody's mean maximal power data or their power duration data pulled out using WKO 3. Plotted with time or duration here on a linear time scale, or very early on, Hunter and Kevin made the very wise decision back in the cycling peaks days to give the option of also presenting it on a log axis, which allows you to get a little better view of the early events that are buried when you have it jammed all the way up against the y-axis like that. So that's what I mean by the power duration relationship. The new model, in a lighthearted moment, when I'm in a good mood, I refer to it as a heartwarming tale in which the mean maximal power chart and the power profiling table meet, fall in love, get married, and have a child that turns out to be somewhat of a child prodigy. Unfortunately, you're all muted, so I can't hear the, the raucous laughter that follows on that. In my more serious, more egotistical moments, I lay it out this way. Implemented in 4.0 is the most advanced mathematical model of the exercise intensity duration relationship that has been developed to date. Now that sounds rather egotistical, I'm sure, yet I know any of my scientific colleagues out there would vouch for me when I say that I'm not prone to over-exaggeration. So when I have a sort of in-your-face comment like this, I'm hoping to shake people up a little bit. Or, as they say in Texas, it ain't bragging if you can back it up. So my goal over the next few weeks is to prove to you that I'm not bragging. But in order to do that, you really need to understand a little bit about mathematical modeling so you know where I'm coming from with this. And that's going to be the topic of tonight's discussion. Before we get into that, though, well, as I was saying, tonight will be a primer, a very short primer on mathematical modeling, so you can at least have some basis for which to evaluate various models that are put before you. In part two, I'm going to take some of those ideas and show you, as you step through, the limitations of presently available models, which is what led me to try and improve upon them. So in part three, I'll introduce my new approach. And then finally in part four, we'll get into about actual present and even possible future applications of the new model. But again, like I said, I know everybody's chomping at the bit and is really anxious here. So just to give you a, oh, sorry, I always get ahead of myself. The $64,000 question, though, is why? Why do you need a mathematical model to describe the power duration relationship, or the mean maximal power curve, if you will? What is the benefit from that? And this is actually something that was a question that was posed to me by other members of the team when I was originally sharing this idea. And that is, unlike many sports, cyclists, at least those who use power meters, have a pretty robust, rich data set recording what they do on a second-by-second basis. So we have a lot of data points describing the relationship between power and the duration that it can be maintained. And if you really want to just smooth this curve by drawing a line, what do you need a mathematical model for? And you could just connect the dots by hand and have an equally good or almost equally good representation, really. There are, however, a number of benefits to actually having a robust mathematical description, and that is it gives us a quantitative insight. No more just looking at the shape of the curve and saying, well, this person's curve looks different than that person's curve. We now actually have ways of pinning numbers on it, which is a deeper level of understanding than a more qualitative sort of impression. But the other aspect to it is that a robust mathematical description of that power duration relationship is really the foundation or the underpinnings for a lot of other things that you'd like to be able to, that I'd like to be able to do with the data. So to give you an idea of what that's about and where all of this is headed, I'd like to introduce to you what I referred to as my Parthenon figure. And I posted a teaser like this up to Facebook, and somebody accused me of very poor drawing skills. And yeah, okay, I'm not an artist. I'll be the first to admit that. I'm too much of a concrete thinker. But this is my attempt to represent a Greek temple, if you will, where the power duration model at the bottom is the foundation upon which a lot of these other ideas that we're going to be rolling out in the future are based. One of the most obvious practical applications of being able to do a good mathematical description of the power duration relationship is to get an automatic or a objective estimate of somebody's functional threshold power. I mean, it's a standing joke for those who have frequented the wattage list for years that the most commonly asked question is, what is my FTP? To which such a common question that I think it was Rick Murphy who once said that, if you have to ask the question, it means it's higher than what you really think it is. But obviously, this is an issue for many people, uncertainty with respect to what their FTP is, and they're unwilling to do strenuous formal tests to determine what it is, or they're in a situation where it's not really easy to do good testing because of whatever environment they're operating within. So having a way to try and extract that data or that number from the existing data automatically is very useful. Other aspects, though, are that other parameters of the model the new model are what I've referred to as functional reserve capacity and Pmax, or maximal power, which we'll be talking about in the future. And related to that, there's the possibility of even calculating changes in functional reserve capacity on the fly, or a dynamic FRC, DFRC, which I've shown you up here at the top here, which is an idea I started playing with, I guess back in 2007 when Alex Simmons, hi Alex, I'm sure you're out there, Alex Simmons approached me with questions about maximal accumulated O2 deficit and whether that idea might be applicable to team pursuit. And whether or not you could determine whether somebody cracked because of pacing strategy or some other reason in a team pursuit. So if you want to dig back through the archives of the Waters list, you can find some discussion of those ideas there, or as is his way, Alex actually does a better job of explaining these things than I ever do, so I just point you to Alex's blog. Well, once you have these quantitative descriptions of somebody's power duration relationship in terms of their Pmax, their FRC, their FTP, that leads right into the ability to do automatic phenotyping of a rider. And I hate to make the analogy because it's not a pretty one to think about, but you know, you could talk about police officers doing racial profiling. Well, mathematically we can do rider profiling or rider phenotyping. No more looking at the power profiling tables that I've put out there and trying to sort of guess, well, is this an inverted V pattern or is it more of an undifferentiated W pattern? It's now possible with enough data available to set up definitive objective criteria by which to define somebody as, are you a sprinter, are you a pursuiter, etc. All of this is also the basis for the idea of generating individual adaptation scores. And you notice the attempt to italicize the S there, which in turn would then become the inputs to a new model of the relationship between training and performance, which is based on attempting to model the adaptive process itself and not stresses that are being applied. Now, as was the case with the idea between TSS and normalized power, it was actually the desire to pursue this direction, which I've been working on, I guess, at least 8 years. And again, you can dig back into the wattage list where I started talking about why I called it training stress score and not training adaptation score, and the subtle but important distinction between those two, as well as even hinted at some thoughts as to what sort of shape I thought a training adaptation score or scores might have. You could dig back about 8 years and find those posts. But it was the desire to pursue this that leads to the need for this, which in turn leads to the need for all of these things, which is why we need a robust mathematical description of the power duration relationship. Altogether, what we're talking about here is a new, more individualized approach to power-based training. What I proposed before is individualized in the sense that TSS is anchored on a person's functional threshold power, and hence coaches are able to look at those numbers in terms of, at least on paper, a TSS score of 175, for example, should mean the same for every rider, at least in theory. But it's individualized only in this, it's on that single anchor point. Whereas if we expand our thinking and instead of worrying about just that one single anchor, we can actually get a more individualized description of somebody's strengths and weaknesses and take that into consideration in doing any kind of modeling of the relationship between training and performance. In terms of where everything's headed, big picture, the next 4 weeks we're going to be talking about this power duration model. The things I've shown here in bold have already been implemented in 4.0. The things that are in gray or light, not bold in font, are still under development, and they'll be implemented down the road. When and if and or when they pass muster from my perspective. They may never make it if they don't live up to my standards. But nonetheless, this is where we're headed over the next few years. The good news is, and I've been told I should share this with all of you, is that although we've only got some of these implemented in 4.0, as we roll out upgrades to 4.0, 4.1, 4.2, et cetera, all of those will be free upgrades. So I think, again, I made a joke on Facebook, or maybe it was in a web forum, but when I look at this, I'm reminded of the scene in the Harry Potter movie where they're in the night bus and the shrunken head talks to the driver and says something along the lines of, hold on to your hat, Ernie. It's going to be a bumpy ride. So yeah, things are going to be changing. What you think you know is going to evolve. And again, to give you some idea of how things are evolving and where we've come and where we're headed, in 2003 I put out the idea of power profiling, which was tables generated based on 4 durations picked firstly for their physiological significance in terms of how they should at least theoretically relate to various physiological abilities, and then secondly picked on the basis of convenience, in that they link to common competitive durations in different events. And that gave us our power profiling tables. In 2010, Hunter proposed expanding that to 12 durations, because having looked at thousands and thousands of such mean maximal power charts, if you will, he's seeing differences in the shapes of these curves that he wants to be able to interpret. So he proposed fatigue profiling as a way of getting greater insight, and it hasn't gotten the following that I think it should have, because it was a very insightful move on Hunter's part. But again, to come back, we as cyclists are in a rather unique situation among athletes, and that we have so much data to deal with. So my thinking was, well, why stop with 12? The power duration modeling and the idea of doing rider phenotyping is leveraging the fact that we have these multiple measurements over a broad span of durations. So attempting to take advantage of all of that information and not just cherry pick specific data points to do calculations. I did in earlier in-house presentations describe this as power profiling on steroids, but given all the bad press that cyclists get for doping, I decided, maybe I should steer away from that analogy. Anyway, so that's some of the things that you can do once you have a good power duration model. But there are other applications as well. The possibility of setting up objective statistical criteria that you could automate match finding. The idea that we only have so many matches that we can burn during a race, and when we're done, we've burned up all the matches in our matchbook. If you've got a good description of the power duration model or the power duration relationship, that gives you a basis for defining what is or is not a match in a robust manner, and therefore lets you set up computer programming to go out and just pick those things out for themselves. Another advantage of having a good description of the power duration relationship is it makes it easy to identify outliers. And these could be outliers in the sense of, well, your power meter wasn't working properly, or they could be outliers in the sense of it was a breakthrough performance. It would take further investigation to determine what the explanation might be. But nonetheless, having a smoothed function makes it easier to determine which points do fall off the line. And you could continue that as far as, if you wanted to put 95% confidence intervals around the predicted power at any particular duration, and then look at points that fall outside of that confidence interval. You would think that a simple eyeball analysis would be sufficient, and sometimes it is. But I've been impressed in analyzing various mean maximal power data or power duration data sets that have come my way, how often people will have outliers that are obvious once you do a little bit of modeling the data that they haven't recognized. Another potential application for the power duration model is the calculation of optimal pacing strategy. And this is something I played with, who knows when, 10 years or so ago, that, again, Alex developed in, to an even greater degree. But the notion here is if we know the physics of cycling, we know the course, we know the environmental conditions, you can derive at least a theoretically optimal pacing strategy that would allow you to arrive at the finish line, say in a time trial in the shortest period of time, given a particular function as the motor. And when I first started doing that kind of thing, it was heartening to find that simply using normalized power as a global constraint was often sufficient to arrive at very realistic pacing strategies, in that they agreed very nicely with what experienced cyclists actually did. But there are cases where the theoretically optimal approach is beyond what the person is actually capable of delivering if you're using just normalized power as a global constraint in your modeling. So some people have done, and I've also played with, using the critical power paradigm that we'll talk about later tonight, to constrain how much power somebody could put out on any particular segment. Well, you could carry that even further and say, well, if we have a robust mathematical description of the entire power duration relationship, then you could use that as a constraint in calculating optimal pacing strategy. And finally, there are potential applications to other sports. I'll show some examples, probably the I don't know, week 3 or week 4 or whatever. But I have taken this model and I've modeled world records in running, world records in swimming, world records in speed skating, and the model is grossly over-parameterized in those cases because, unlike cyclists who measure their power second by second, you're just dealing with discrete time points at various durations. And of course, they don't represent a single individual, right? Because you don't set a world record in the 100-meter and also the marathon by the same person. But nonetheless, the model will fit that data quite nicely. I've looked further. I've tried to find if there were any decent records for dog racing or for pigeon racing, but so far I haven't found any data sets that I think are trustworthy enough. So if anybody is aware of any data out there, I'd be interested to try and apply the model to those as well. So with that as a very lengthy introduction, in order to me prove to you that I ain't bragging, it's important that you understand a little bit about modeling and how one goes about constructing and especially evaluating mathematical models. And so that's going to be the rest of the talk tonight. Now, you might say to yourself, well, who are you to be telling me how to model? And it'd be a valid question. So at the risk of sounding egotistical, just to give you a little bit about my background, I am an exercise physiologist by training, and it remains my first love. But contrary to what many people seem to believe, I am not, nor have I ever been, an applied sports scientist. In fact, the last research study that I did in which performance was an outcome variable was my dissertation, which was a long, long time ago now. Instead, I spent about the last 20 or some odd years in the medical school environment, living on soft money, aka grant money, more as a metabolic physiologist, trading on my background in stable isotope and now in general isotopic tracer methodology. So my introduction to mathematical modeling then was when I was at University of Texas Medical Branch, Bob Wolf's metabolism unit in the Shriners Burns Institute there. Bob had put together actually a PhD program on mathematical modeling to train people in this area, and recruited me to the program because he also wanted to expand into exercise stuff. So that was in the mid-90s, well actually early 90s, 92 is when I moved there, is what my first exposure to mathematical modeling, because it was sort of a wave that washed over the stable isotope realm. Last 10 years, I've spent most of my time in the cardiovascular imaging laboratory here working with compartmental models of positron emission tomography. So going from dealing with stable isotope tracers, which don't decay at all, to positron emitting tracers, which decay very rapidly. But it's the same techniques, and that is compartmental modeling. You have a bolus, a tracer, and in fact, the hat I wear around here as the stable isotope person, as I like to joke, is I'm the stable one among my colleagues. So we do various research studies trying to use PET to look at cardiac metabolism in various physiological and pathophysiological states. And while I remain a physiologist by training, I have had the pleasure then, over the last 20 years working with a number of modelers, David Chinkus, Judah Rosenblatt in Galveston, and my good friend Pilar Herrera, who was here at Cardiovascular Imaging Lab until she recently retired. So I've picked up enough about modeling to not be dangerous, and that is to not make any silly mistakes. I've taught mathematical modeling techniques and tracer techniques in American Physiological Society sponsored symposia on kinetic modeling, and I've also taught a course to postdocs and fellows here on these kinds of methodologies. Anyway, what I learned along the way, caveats that I want to share with you when you're talking about mathematical modeling, important things to keep in mind is that you can develop mathematical models and you may have great confidence in them, but you can never forget that these are theoretical constructs. When we talk about our compartmental models, for example, you can draw a compartment, you can generate all kinds of data that suggest that your model is correct, valid, whatever terminology you want to use, but that doesn't mean that compartment really exists in reality. What you have is a mathematical representation of the data. It's the best one you hope to come up with. It seems to be correct at the present time, but it's possible that new knowledge could come along and prove that that was an incorrect conceptualization of the system at hand. More bluntly, it was George Box, George is his first name, I believe, statistician, put it as, all models are wrong, but some are useful. And again, an analogy I would draw here is sort of like getting audited by the IRS. If you're lucky, you'll get a tax examiner who will interpret the IRS codes one way, and they'll agree that your deductions are, perfectly acceptable. And if you're unlucky, you'll get audited by an examiner who doesn't think that your deductions are permissible under the law, and you'll have a big tax bill to pay. It's similar when it comes to evaluating models, in the sense of, beauty is in the eye of the beholder. The ultimate question is, does the model work for what you want it to do, or doesn't it? Now, that said, some models work better than others, and the usefulness of any model depends in part upon what I refer to as its domain of validity. So rather than thinking about models as being right or models as being wrong, the question is, well, under what conditions do they work well, and in what conditions do they break down? And here's an example of that. Excuse me while I pause here for a sip of water. This is a study we published a few years ago attempting to validate a long-standing mathematical model first proposed by Bergman, a PET model of cardiac lipid metabolism that had been validated initially in many of its components, but one of the aspects of the model is the calculation of the rate of incorporation of fatty acids into neutral lipids, triglycerides, but also membrane lipids, phospholipids, etc. And this has become more important from a physiological and pathophysiological perspective with the recognition of what, at least around the WashU environment, is commonly referred to as lipotoxicity. The concept that an oversupply of lipids in the form of non-esterified fatty acids to tissues that are not really designed to deal with them in such large amounts leads to deleterious effects on cardiac function, on liver function, on skeletal muscle function, etc. So we were interested in attempting to validate the calculation of myocardial triglyceride synthesis based on this non-invasive PET imaging technique. And so we did studies in dogs in which we were able to compare the PET myocardial fatty acid esterification rate, MFAE rate, so the PET model derived data against directly measured rates of triglyceride synthesis in the hearts of dogs based on the incorporation of stable isotopically labeled fatty acids. And if you look, we got a statistically significant correlation between the two measurements, as you should have. The slope of the line, however, is significantly different, significantly greater than 1. Y equals X here. Ideally, all of your model measured data would fall along this line of identity. But instead, MFAE overestimates the rate of triglyceride synthesis, probably because it also reflects incorporation into amino acids and via TCA cycle intermediates. Still, with that in mind, you could still learn something potentially by applying the PET model under conditions in which it is valid, with the realization that you're measuring more than just triglyceride synthesis. You're measuring something that is, but is nonetheless correlated with triglyceride synthesis. Now, in order to generate a very large range in the metabolic state, the dogs were studied under a variety of conditions. So if you actually look more closely here, this is a blow-up of the small part out to 150 nanomoles per minute per gram of heart tissue. The open circles represent all of the conditions in which the heart was at rest. The closed circles represent dogs that were infused with dobutamine to increase heart rate and hence cardiac work. And what you can see is that although the model works fine in the resting animals, regardless of whether they're infused with intralipid or a clamp or if they're just studied after an overnight fast, there's no relationship between the directly measured rate of triglyceride synthesis in the dogs that are infused with dobutamine and the PET estimated rate under those conditions. The reason being that when you increase cardiac work, or at least the likely reason being, when you increase cardiac work, you increase the rate of flux through the TCA cycle, you alter the probability of the tracer ending up into amino acids and other spin-off products of the TCA cycle versus the probability that will end up in neutral lipids. So the model is valid, but its domain of validity seems to be limited to the resting state. And when you move away from the resting state, the model breaks down. Which brings us all the way to the point of, well, how do you evaluate mathematical models? Now what I was talking about right here is really the most direct approach, external validation, which is what we've done, or historically have done here a lot the last 10 years or so. But with the drying up of the NIH budget, that kind of stuff isn't readily fundable anymore. So we're having to look elsewhere for research support. It's an unfortunate fact that lots and lots of people produce models, but they never actually get around to validating them against any gold standard sorts of criteria. And of course, there are cases in which, there are many cases in which that's not possible. You've got some, you're modeling some process because you can't measure it directly. There are, however, other situations where you can, and ideally you should, perform an absolute verification or validation of the model. To back up, though, when you're first, putting together a model, and it can either be a purely empirical sort of model, or it could be one that's infused with a priori knowledge, such as, you know, how physiology works. Regardless, there are statistical criteria that can be applied to say, well, is this a good model? Do you have a good description of the system, or do you not? An F-test can show you overall whether you've got, you know, more than a random number generator. You can apply the runs test to look at the residuals to see if there's any inherent structure in the error, or I guess it's a structural error that leads to non-random distribution of residuals. If you're dealing with nested models, that is where each model is a subset. All the models are from the same set. Models are subsets of some parent model. Then you can use the AIC, the Ikeki information criterion, to try and decide, you know, which is the best model. But these statistical criteria are really aimed more at evaluating specific aspects of a model or specific assumptions of the model, and not really globally at the model overall. And so the real workhorse when it comes to actually evaluating models is a lot more often is just simply graphical analysis and quantitative analysis, what are referred to as the residuals. And I'll talk about that in a second here. But one thing you'll notice is not on that list is you see I haven't listed the R-squared value as a measure of the quality of a model. And if there's anything I hope you remember from tonight is that you can't rely on the R-squared alone or even at all to tell you about the goodness of fit of a multi-parameter nonlinear model. The reason for that is R-squared has a different meaning in this situation than what you're probably most familiar with. Well, let's think about a set of data here. It's a scatter plot of some, you know, variable measured on the y-axis versus some variable measured on the x-axis. I'm sure you're all familiar with the idea of linear regression, in which you can, you know, write an equation y equals a plus bx and calculate the intercept a, the slope b, and also the correlation coefficient, or in this case r squared is the coefficient of determination. And in this context, it tells you what percentage of the variance that the two variables have in common, or another way of phrasing that is what percent of the variation in y is explained by the variation in x. The unfortunate aspect is, though, when you're talking about nonlinear modeling, is you can always get a bigger r-squared by just adding additional terms to a model. In fact, if you want to just do a polynomial fit here with 7 data points, you can get a perfect r-squared of 1.00 by including 6 terms. So just keep chucking additional terms into the model. You can keep inflating the r-squared value. Doesn't necessarily mean that your model is fitting any better. It's also theoretically possible in the case of nonlinear fits to go the other way, and that is the r-squared value can even be negative because it's calculated differently than in the case of a linear regression. And if you remember your high school math, the only way you can square a number and get a negative value is if you're dealing with imaginary numbers. So the r-squared itself is not really what you're after here, and yet quite often that's all people will report, as if they want to impress you with the quality of the modeling they've done by giving you an r-squared value. Now, there are ways of adjusting this r-squared for the number of terms in a model, and if you've ever done any nonlinear curve fitting using any sort of statistical software, it's quite common for the output of such calculations to include the adjusted r-squared. But the fact of the matter is that these adjustments that are made to try and account for this over-parameterization, if you will, are inadequate. And that is, if you've got a multi-parameter model, you're almost always going to get a high r-squared value, and it doesn't really tell you about the goodness of fit. So if we're not going to look at r-squared value, what are we going to look at? As I was starting to get to, residuals are the most common way to do a graphical analysis of the residuals, to look at their magnitude. And that is, how closely does your fitted function come to the directly measured data. You can also look at the distribution of the residuals. And that is, if you've got a good model, they should be randomly distributed around 0. Sometimes high, sometimes low, but with no overall bias one way or the other. And then finally, you can plot your residuals against the variables you're using in your modeling to see if there's any bias involved. Again, a good model, the residuals of your calculations should be independent of the inputs and randomly distributed with respect to the input. And again, I'm getting ahead of myself here. What do I mean by residuals? In particular, normalized residuals. We're simply talking about the difference between, the observed value, the predicted value, divided by the observed times 100% here. So it's the residual, the leftover, the difference between your observed and your predicted, and then normalized to the observed value. And again, the example I would draw there, if you want to think about it, you might have a model that predicts your sprint power to within plus or minus 10 watts, which even if you're a very poor sprinter such as I used to be, would still be within plus or minus 1%. But that same 10-watt error, if it were talking about your functional threshold power, would be a much larger relative error. So by normalizing things, you're making them relative to the measured values. Graphically or schematically, I guess, this would be an example of the residuals of that linear fit I was showing you earlier, and that is these differences here between the measured values and the predicted line. And of course, this is what you're trying to minimize when you actually fit either your straight line to this sort of function or to a nonlinear function to some more complex system. And I guess I should make a point here that I'm not going to go into how you actually go about solving, either creating or solving mathematical models. It's sort of beyond the scope of this series of webinars and what I hope to convey to all of you. What I really want you to have some appreciation of, I would say, is how you go about actually evaluating different models. So when you're presented with a model, either from me or read it in a paper, you have some basis for there saying, does this model make sense or doesn't it? Or are they not telling me enough to really know? So we can look at the magnitude, the distribution, the bias of the residuals. You could have a very good model, but you also have to consider your parameter on the basis of the residuals, but you also have to consider your parameter estimates. And that is, how many parameters have you included in the model? To go back to my linear versus polynomial example, the linear model has 2 parameters, right? A slope and an intercept. Well, that polynomial function had 7 parameters. 6 terms, including x plus an intercept or a constant. And again, you can always get a better fit by including more and more parameters, but that doesn't mean that you really should be including all of those parameters. The limit to the number of parameters that are justifiable is something that might be a little bit open to debate among statisticians, but the rule of thumb that's been put forth is that you need 5 to 50 observations per parameter. So if you're trying to fit a 4-parameter model, for example, you would need 20 to 200 pieces of data. Now, the good news is if you're trying to model the power duration relationship of somebody who uses a power meter and it's set to record at 1-second intervals, you've got a lot of numbers to play with. So over-parameterization isn't such a great concern, I don't think, in this particular situation. But it would be if you're trying to, say, model running performance where you don't have that sort of wealth of data. Another consideration here is the independence of your parameters, and that is you may include 2 parameters, and by including, like say, 2 particular parameters, let's say you might try and predict somebody's success in college by including their IQ score on some standardized exam and their high school GPA. Well, the more parameters we put into that model, then the greater the ability will be to describe reality will be. But I think you would agree with me that there's a good likelihood that somebody's IQ on an IQ test and their high school GPA would be correlated with each other. And so then the question becomes whether or not it's statistically justifiable to include them as two independent parameters, or whether they're really so tightly related that you should really just lump them all in together. One way of looking at of addressing that issue is to look at a correlation matrix of your various parameters and seeing which things might be correlated with each other, and then ask yourself, well, is this is this to be expected, or is it simply a case of overlap? And I'll come back to that when I talk about the new power duration model a little bit more. Another thing that can be done, and this overlaps also with 3C there, and that is to look at the precision of the parameter estimates. It's all well and good to fit a model, and it tells you that your FTP is 287 watts, for example. But is it 287 watts plus or minus 3 watts? Or is it 287 watts plus or minus 30 watts? Obviously, without that additional knowledge, you don't have a basis for really evaluating just how well you've tied down your estimate of that particular parameter. If you carry that thought then to the extreme, you can actually then, I guess not the extreme, but to the logical conclusion, it's then fairly easy to understand if the confidence limits, the imprecision on a parameter estimate overlap 0, then it's not really adding anything to your model. You've included it in there, but in reality it might as well be set to 0. Now that could be because the parameter doesn't really belong in the model. It could also be, however, that there's just so much noise in your data that you can't extract a really tight estimate of the parameter, the value for that parameter. And this loops us full circle to some of those models I showed earlier. When we do these PET experiments, the PET scanner operates in what historically has been referred to as list mode and measures the decay of positron-emitting atoms with very high temporal resolution. So you have lots and lots and lots of data, so much that it actually has to be binned in order to reduce the number of data points that you're dealing with, or usually is a bin to reduce the number of data points that you're dealing with. Even so, the shapes of the washout curves may not be distinct enough for you to extract what you want to extract, such as calculating the rate of lactate formation from glucose taken up by the heart. At that point, you either give up and say, well, it just can't be done. The data are too noisy. The signal isn't strong enough. Or you can also say, basically, the ends justify the means, right? All models are wrong, but some are useful. You can sit there and say to yourself, being able to measure this quantity would be very, very useful. Therefore, how do I go about doing that in the face of this difficulty with a signal to noise? And one thing you can do is perhaps constrain your parameter estimates. So when your computer software is searching for a solution to a particular system of equations that are supposed to describe your mathematical model, you can dictate that, well, I know this value will always be between x and y. It will never be, greater than X. It'll never be less than Y. So constraints can be used. And in fact, that's what we did. And as I was talking about, if you go back, and I won't back up, but if you go back and you look at the one model I showed, where it's actually a pair of models, we were trying to model the details of glycolysis in the heart based on administration of an 11C labeled glucose tracer. And Pilar's approach was 2 steps. She had a reduced model that she applied to the early phases of the washout curves obtained with PET imaging techniques. And then once she had those parameter estimates, she then fixed those parameter estimates and solved for the remaining parameters in the more complicated, more extensive model. But the bottom line here is that knowing the precision of parameter estimates is very important in judging the quality of fit of a model. And if people don't provide that information, then you're kind of, lost in the dark. And then finally, I was talking about external validation, very important if it's possible. So I've been talking about PET stuff and tracer modeling and kinetic compartmental modeling, and I was actually going to then try and walk through one of these models as an example of just how you use some of these criteria to evaluate the quality of your model. And then I decided, well, I'm going to lose everybody at that point. None of you are interested in that. You're interested in cycling and cycling power output and how to win bike races, right? So I decided what I would do would be to jump ahead a little bit into week 2, actually, and talk about the critical power model and evaluate it using some of these methods just as a way of illustrating the approaches. I don't want to be I don't want people thinking that I'm picking on the critical power model. I used it simply because it's one of the most well-known, and despite its simplicity, is actually rather robust. That is, its domain of validity is, it does, well, I wouldn't say it's wide, but it certainly is a pretty good model of the power duration relationship under the right conditions. So what is the critical power model? It was first mathematically introduced by Monod and Scherer in 1965, where they're dealing with isolated muscle exercise, and then Moritani et al. Applied it to whole body exercise in 1981. You can go back earlier than that, where people were drawing these kinds of hyperbolic curves describing the relationship between, how fast somebody could run and how long they could run, but without the sort of mathematical formalism. And it's since been extensively tested under a wide variety of experimental paradigms, and a number of wrinkles have been introduced along the way, as we'll talk about next week. But in its original form, as shown here, the critical power model postulates that your power at any time t, shown by the blue line, is a function of what was originally termed anaerobic work capacity. Now people are just liking to call it W prime, divided by t, plus some critical power. So critical power is supposed to be represented by this red line here. And as you might surmise from the equation, at very long durations, power decays, or at longer durations, power decays to critical power, but it never decays below critical power. And at shorter durations, this W prime divided by T is a work capacity, which I've attempted to represent with these boxes here, which in theory all have the same area, right? So there's a certain amount of work you can do above critical power. The more rapidly you're doing that work, that is, the higher your power output, the sooner you fatigue. The more slowly you're doing that work above critical power, the longer you can last. There are other mathematically equivalent expressions to the model. You can linearize this by plotting work against time instead of power against time, etc. But this is what we're dealing with here. or the way I've presented it here. So let's think about this model. In order to provide some evaluation of it as well as the other models, I've analyzed a very large number of power duration data sets from almost 100 seasoned athletes. That is, not 100 athletes, not 100 seasons, but the combination thereof. And individuals ranging all the way from age groupers to those at the very pinnacle of the sport, and in disciplines ranging from match sprinting to 24-hour time trial and Ironman distance triathlon kind of thing. So that's my test data set here. I then took the critical power model, as I showed you in the previous slide, and I analyzed all of these power duration curves using it based on all of the data between 1 and 10 minutes inclusive. Because in laboratory-based studies where you're doing formal tests, people normally restrict themselves to tests of those durations or similar durations. So just looking over that time period and then looking at the distribution of the normalized residuals, things look pretty good. And that is, on average, we're close to 0% error, right? Sometimes the model underestimates, sometimes the model overestimates, but it's a pretty normally distributed function that's symmetric or close to symmetric, around 0. And then if you plot those normalized residuals against the duration of the effort, all of them overlap 0 in terms of standard deviations here. So no real evidence of any bias where the curve really misses high at a particular duration or misses low at other durations. And if you then look at a correlation matrix of the parameters of the critical power model, well, it's only a 2-parameter model, so the correlation matrix doesn't look very exciting here. But we'll have more extensive correlation matrices for other models which have more parameters. But you see there's no correlation between W prime and critical power in this data set. That is, they, as you should expect, they're independent measures here, which is a good thing. You might ask yourself, based on known physiology, why we don't see an inverse correlation here. You might think that, the time trialists of the world would have really high critical powers but low W primes, and the sprinters of the world would have really low critical powers and really high W primes. So you should have an inverse correlation between the two. But in fact, the data set that I have, I was dealing with just raw watts, not adjusted for body mass. So even if somebody's power duration curve makes them a sprinter or makes them a time trialist, if they're big or small, if you're a big person, you're going to tend to have a higher W prime in joules, just like your critical power in watts will be higher. And if you're a small person, your W prime in joules will be small, just like your critical power would be. So that may be why we don't see an inverse correlation. In any case, they're independent parameters. And I didn't bother to make a slide showing the I didn't bother to make a slide showing the precision of the parameter estimates, but they were typically 1 to 2% for critical power and around 3% for W prime when fitted to the data between 1 and 10 minutes inclusive. So pretty good fit, pretty precise estimates of the parameters. They're statistically independent from each other. No evidence of bias based on the distribution of the residuals or plotted against time. Everything's hunky-dory, right? Then you start thinking about external validation, and you look at the critical power, which is supposed to represent a power that, quote, can be maintained for a very long time without fatigue occurring. Now, that certainly sounds like the sort of power that one would maintain for a time trial, right? And I have time trial data for a subset of all of the cases that I analyzed here, which, by the way, I excluded from their power duration curve in order to avoid any sort of autocorrelation problems. But if you look at the critical power and you compare it to their TT power, yeah, it's correlated just like you'd expect, and just like it, may have been reported in the scientific literature, although offhand I can't recall any study that has actually done critical power in the lab and looked at road TT, but I'm sure somebody's done it for a master's thesis. So yeah, you do have a statistically significant correlation, but as you can see, the critical power is on average higher than the power that somebody can actually maintain during a time trial. The intercept there is not statistically significant from 0, but the slope is statistically different from 1. So we have evidence here that the model is biased in the sense that it's not predicting reality the way it should be, or the way that we would hope it to be. And of course, that's really not surprising. If anybody has looked at these sorts of curves, critical power model is a right rectangular hyperbola, which looks pretty much the same on a linear plot and a log plot, whereas the mean maximal power curve, or the true power duration relationship, doesn't really look like that. So you might be able to adequately describe the true data over a limited range of durations using the critical power model. But remember, the whole point here was to try and take advantage of the fact that we have this rich data set all the way from 1 second out to 20,000 seconds, in some cases 30,000 seconds in some subjects. And the critical power model can't do that. It breaks down once you get beyond, or once you go beyond a certain duration, or when you're talking about shorter durations. And so if you take the that same values for critical power and W prime derived from the 1 to 10 minute data, and then try and look at the distribution of the residuals across the entire time span, no longer do we have this nice normal distribution centered on 0. And that is, in the vast majority of cases, the model overestimates what somebody could do. Another way of looking at the same thing, basically, these are the normalized residuals versus duration for the critical power model, calculated based on data between 1 and 10 minutes inclusive. And if you use those time limits, which are what are used, for example, in the method that's implemented in Golden Cheetah, and like I said, in the vast majority of lab-based research studies, people are focused on that time frame. Yeah, the model residuals overlap 0 over part of the curve, but once you get out beyond, this is just a little bit beyond 10 minutes, I believe, things start to go, they don't go south, they go north, right? And similarly, at shorter durations, the model overestimates what somebody could do. Now, that's not news and shouldn't be news to anyone. And again, I don't want to seem like I'm picking on the critical power model here. I brought it up just because I figured people would be familiar with it, and it gives an opportunity to illustrate how you evaluate models. But again, this shouldn't be news. When I first brought up the critical power model on the wattage list over 10 years ago now, I made the point. It's not without its limitations. It tends to overestimate the maximal power that can be generated for only a few seconds, and it predicts that there should be a power output below which fatigue will never occur. As a result, or in addition, the exact values you get for W prime and critical power depend on the testing protocol. That is, the exact combinations of powers and durations used to define the curve. And if you indulge me here, I'll jump back a couple. If you just think about this, instead of using 1 to 10 minutes, we could say, well, we really want to use, say, 3 to 30 minutes. And what that would do would be to shift this blue curve to the right, and it might fit over a different span of the data. But you could also use, say, 30 seconds to 5 minutes, and you could shift the curve to the left. So the model is sensitive to the particular values you use to calculate it. So to summarize tonight's talk, and like I said, I wanted to try and keep things short so I can keep people focused and handle any questions. But to summary, modeling the power duration relationship has many potential benefits rather than just relying on a graph to instead develop a robust mathematical function. But the only way that's going to work is if you have a decent model. And we've talked a little bit about what sorts of criteria and approaches you can use for evaluating potential models, and these do not include R-squared. And the classic critical power model fails to adequately describe the entire power duration relationship, that its domain of validity is limited to a particular portion of the entire span of human performance ability. So with that, by way of introduction and background, next week we're going to go on and talk about other possible candidate models and evaluate them from the same sort of perspective. At this point then, I've presented everything I wanted to present tonight, and I can stop and take any questions or take some questions here. Tim, are you out there?
I am. Hi, everyone. I'm going to facilitate some questions. The good news is, as most of you have been watching in questions while Andy has been presenting, I've been pretty able to keep up with all the questions in the background. Obviously, with this presentation being an overview on modeling, the questions haven't really dug into the specifics of what we're doing because that process overview really starts next week. Please feel free to type in any final questions in the box. In your questions box, most people have figured out how to use it. If there's no further questions, then we can close it up for the night. As Melissa said, the recording will be available. Oh, wait, here we come. Now I'm in trouble. Okay, so Andy, here we go. Let me just look through a couple. Here's a good one for you. If you are using all the power data, wouldn't the power duration model also be highly dependent on how someone trains?
Yeah, you might call this the GIGO problem: garbage in, garbage out. So the reason I present it that way is you really need to draw a distinction here between limitations of a model and limitations of the data that you're attempting to model. So, the classic example might be, let's say somebody spends 3 months in the winter doing nothing but ride the trainer, and never once do they give it full shtick for a very short duration, and never once do they do a maximal 5-minute VO2 max interval, and never once do they do a really hard time trial type effort. Well, of course, their power duration data from that block of training is going to be an underestimation of their ability. And if you then fit a model to it, it's not going to reflect their actual strengths and weaknesses. But again, that's a limitation of the data set itself, not a limitation of the modeling approach. The thing that also comes to mind whenever people bring up that aspect is I'm always reminded of Jack Daniels, the running coach's position, where running paces in his system are based off of your V dot. Estimate of your VO2 max, basically, which is calculated from your performance in various races. And so people get enthusiastic, chomping at the bit. They're feeling good in training. They want to run faster in training. And his response to them is, if you want to train harder, first you have to prove it by racing faster. Of course, there's injury risks in running that you may not encounter with cycling that would make a more conservative approach perhaps a better way to go. But it does illustrate the point of these kinds of calculations, and that kind of thing are very much what have you done for me lately is what it comes down to. So if you have a data set, you fit the model, and you don't believe the results, the solution is prove it wrong. Go out and do a hard workout. Or just accept that, as with anything in life, you have to interpret model data in the context with which the data, or model outputs in the context with which the data are collected, and just realize what the limitations would be and go from there.
Excellent. And Karen, great question. I would add only at this point is a superior model would do a good job with the least amount of information, and that would be part of the reason we would want to model. So I understand your questions because I see the series of your other questions which will be answered in future webinars. Two other good ones that are in here, Andy. Could you comment on the quantification of uncertainty in a model of your confidence interval? I'm sorry, the type is so small here. The model predicts plus or minus with 90%, e.g. the model predicts plus or minus with 90% confidence.
I think this may come back to when you're talking about the precision of the parameter estimates, which is what we're interested in here. Usually those are given as standard deviations, but of course you could convert them into 90% confidence intervals or 95% confidence intervals, etc., if you wanted to. I think that may be what the question is getting at. Now the other way of looking at it is, the root mean square error of the model, and that's based on how closely the fitted function comes to each and every individual data point, say on average, a central tendency measurement there, using it in that term. That's a way of comparing one model to another as long as you're modeling the same data sets. But in the context of what we're attempting to do here, the precision of the parameter estimates themselves is as much, if not more, important. It sort of depends on the context, I guess. To come back to, I was talking about trying to do theoretically optimal pacing strategy. Well, in that case, the consideration would be how closely the fitted function comes to the actual data at any duration. Whereas if the question were, well, how closely can you estimate somebody's FTP on this basis, well, then it comes down to the precision of the parameter estimate.
Excellent. Another really good one, even though, as most people can see, I'm putting kind of a standard answer that you're asking questions that the future 3 webinars will answer. So if you're getting that, I would hope you would tune in to see it or watch the recorded version when we're done. So Andy, just in answering this question, because I saw it a couple of times earlier too in a presentation, what is functional reserve capacity, FRC?
It's the amount of work that you can do above FTP before fatiguing. Now, yeah, I apologize. I know people are champing at the bit to talk about the new model, and yet we have to get through this stuff first, which is why I'm trying to keep it short so everybody doesn't lose interest, etc. But if that definition sounds just like AWC or W prime to you, well, yeah, in terms of words it is. But it's calculated differently, and there's a lot of implication, call it baggage, that comes with the term anaerobic work capacity. I mean, there's a whole literature on it, right? And so because it's calculated differently, and because I didn't want to have people drawing conclusions based on other models that they shouldn't, I chose to call it something else. The analogy I've used here is way back in the day when there was a controversy about anaerobic threshold, now thoroughly debunked, at least I hope so. The point was made by very good scientists that why not just describe what you measured and call it the ventilatory threshold, because you avoid all of the baggage that comes with calling it anaerobic threshold. The assumption that you know what causes it and this is a specific mechanism, et cetera, et cetera, et cetera. So by the same token, FRC, a different term to avoid implications I don't want people to draw. And as I'll show you in week 3, while it's on paper or in words the same as W prime, it doesn't correlate with W prime all that well. So it's different quantitatively, it's different mathematically, and it's a little bit different conceptually, hence a new term.
Okay, and I'm answering some of the questions. We're going deeper on FRC, and I'm giving you everybody the form answer. Andy will go deeper on it as he shows application in future webinars. Sandy, here's a little crystal ball. I'm going to ask you 2 crystal ball questions. So, 1, have you been working on a model that will not only allow someone to see the PMC, but also make adjustments, e.g. including more intervals or zone 5-6 riding time and so on, and see how they could affect future growth? Did you understand that question? It was kind of a run-on.
Have I been working on it? This is sort of like the holy grail that everyone's been seeking, right? I remember having a very a late-night conversation with Dave Martin of the AIS at ACSM a few years ago now, where we encountered each other in the lobby at I don't know, it's midnight or whatever. They're standing there just talking till the wee hour of the morning. It seemed in retrospect. Maybe I was just tired. But he was telling me how they had attempted to model the relationship between training and performance, the AIS had, using the notion of circles of influence. And they had set up a very complicated approach that when they finally tried to apply it, it didn't work. It all fell apart. They couldn't extract what they were after based on the system they had constructed. Yeah, I'm working on it. Yeah, we're all working on it. I don't know how much more to actually say, but I think you get into some sort of deep philosophical sorts of questions about modeling, and that is actually I saw another question here, and this kind of relates to it. Is that are you concerned with the purely empirical, in which case we don't have to know much about the physiology? Or are you going to build your models explicitly recognizing physiology and incorporate that information into the structure? Because unlike modeling the power duration relationship here, where we have these large-ish, I mean, in the era of big data, these are not large data sets. But they're pretty decent data sets when you have a few hundred points, right? Or 100 or 200 points. Compare that when you're trying to look at the relationship between training and performance. How many times does somebody actually measure their performance? Truly measure their flat-out performance in various states of training. I know we all tend to go hard only when we're fit, right? So it's a difficult nut to crack. But yeah. I'm thinking about it. I don't know if that's an answer or not.
That's a fair enough answer. Obviously it is a process. So.
Well, actually, it is a process, and that's one of the things I was trying to emphasize with when talking about that Parthenon figure is that I know where the field, I know where I see things need to go. And I'm trying to push things in that direction, but how long, if ever, it will take to get there, only time will tell. But it's an ongoing process.
Agreed. All right, one last question. I want to get Dan's question here. How much of a problem with the modeling process does the fact that we're modeling a changing system cause? For example, our data set contains fatigue data and also data when we're less fit / more fit.
Could you repeat that?
Sure.
I was distracted, sorry.
How much of a problem with the modeling process does the fact that we're modeling a changing system cause? For example, our data set contains fatigue data and also data when we're less fit / more fit.
Yeah. You know, I think this will probably be best addressed in week 3 or week 4 when I actually, show you application of the new approach. But this actually does relate to the GKO idea. All we have is a measure of somebody's power at a particular duration. We don't know whether it's the most that they can do or if it's less than the most that they can do because they didn't push themselves hard enough or because they were fatigued, as this questioner was raising. That said, by leveraging the entire curve, you hope to mitigate that influence to some degree. And as I'll show, if you have data over sufficiently long periods of time, that is, blocks of training, the model is sensitive to changes in the focus of your training. It's sensitive to tapering, etc., in ways that you would expect it to be. But again, this comes to a limitation of the data and not a limitation of the model. So you need to just keep these kinds of limitations in mind when you interpret the output of the modeling process.
Excellent. All right, so I lied. 2 interesting comments, and then these are the last 2. So great comment from Matt. Should we care how something is done, underlying physiology, or just predict what can be done? An interesting note about models.
I guess it depends on the purpose for which you want to use the model. I'm talking, big picture here. To some extent, by referring to things as functional threshold power and functional reserve capacity, I am saying that for the purposes of winning bike races, the physiology doesn't really matter. I mean, it's really interesting to try and understand why there seems to be this plateau in a power duration relationship before you fall off of it. But from a practical application perspective, it doesn't really matter why it is, it just is. Turn it on its head, though, there are other situations when you're trying to do modeling where a purely empirical approach doesn't work, and you need to leverage other information, such as a priori physiological knowledge, into coming up with a workable approach. The impulse response model is actually a good example of that. When Bannister et al. Set out to develop it, they were modeling their time constants on the basis of known physiological processes, and they found that their models didn't work. And then they had to take a step back and just take an empirical approach. But there is no connection between a time constant of typically around a month or a little more for the fitness gain or the fitness function in the impulse response model. It's just what empirically tends to fit the data.
Excellent. Okay, I'm going to ask myself.
All models are wrong. The question is whether they're useful.
Good point. I'm going to answer this next one. Will there be a forum for discussion and ideas presented in this and future webinars? Yes, there is a forum on TrainingPeaks. There's plenty of ability to communicate through that process. Some here are on the wattage list, which is a Google group, which is invite only. But you can attempt to get an invite. I think the moderator is actually on the meeting. by Google search wattage list and see if you can get on. But there's going to be forums. You're going to see this coming up. This is the leading presentation, so you will see the ability to have input, output. Very, very last one. I think I've been able to keep up with most. Actually, I think I accidentally deleted, but will this model be in WKO 4? Simplest question, right? Yes, everybody, that's why we're presenting it. It will be the core new science feature in WKO 4.
It's the foundation.
All right, Andy, here's a classic question for you. Let's see if you know the answer. It's kind of funny. Someone's asking, what does WKO stand for?
Kevin Williams, when he wrote the original Cycling Peaks, came up with a new file format for the downloaded data, and he needed an extension for it. So the files were WKO for workout files, and that's where WKO comes from.
Everybody thinks it's a fancy something anagram secret message code, but yeah, it was the file extension from the original. Great answer.
Kudos to Kevin.
Yeah. I think I've gotten to most. There's been 1 or 2 requests for resources in the end. So, I've been keeping track of that. 1 or 2 questions that go beyond my ability to even ask you because they're too technical. I copied it. I'll email them to you, and we'll see if we can't tackle them. I'm sure they'll be handleable by you. But I think that wraps it up for the evening.
All right. Well, I thank everyone for their time and attention, and next week we'll dive into a few more models and slowly make our way to the things that everybody are really interested in talking about. So until next week.
Thanks, everybody. Good night.
Thank you.